All right, hey, let's go ahead and get started. Welcome back. Happy Tuesday. I saw some good activity, good progress on your projects, and it just seems like teams are well on their way. I think it can be just very hard to plan out, day to day, week by week, what milestones are appropriate for you. But just be honest with each other as a team and just make sure that everybody's doing their part to make sure that things get done. As you know, as we've experienced, you really can't last minute a lot of these things, right? Maybe software. Maybe you can kind of keep tweaking software until the very end because those build and test times are very quick. But when it comes to hardware, you really need to have the core functionality in place. And then everything in terms of last minute could be small improvements, things you can always roll back and get rid of if they're not really good enough for your purpose. So keep up the work on that. Wednesday's a good time to make a lot of progress on these projects, but it's going to take some push. So find the time as a team, either individually contribute or as a team get together and make it happen. And I think we'll be happy with the end result here. In terms of concepts, we've although we kind of skimmed over some of the very last parts of texture mapping with regards to level of detail and the type of filtering that can happen there, I thought it was appropriate given the amount of, relatively short amount of time we have left this semester to kind of move on to looking at more of the microarchitectural issues as they relate to computation. In terms of the microarchitectural issues as they relate to graphics for rasterization-based rendering systems, we pretty much have covered it. I mean, there's some things that you still would have to experience and design yourself in terms of how texture mapping would work. Anti-aliasing, we talked about it conceptually, but what that means in practice is something that another team is getting to experience as they're doing their own implementation. But otherwise, big picture, rasterization-based approaches with programmable shaders, we kind of have it. So let's now talk more about the compute side of things. It's not really starting over because I think we'll see there's just a natural evolution from what was built up and developed to support graphics and what has been applied to support more general purpose computation. In some sense, very real sense, there's nothing new here. Just kind of a reframing and a recalibration, a reuse of the same hardware we already kind of understand to some extent. So we'll talk about that. There are some new things from a programmer's perspective that I think are important. I'll just give a little bit of history. When I first taught this class, we had a pretty big unit on what was referred to as the time, and a term you may still see in use of GPU. I don't like the term. It's a mouthful. I have trouble pronouncing it. I have to pronounce it very slowly to get the letters out appropriately. But it stands for General Purpose Computing on Graphics Processing Units. There's no standardization board that determines what things should be called, so you may still hear that term referred to today. The idea is, as the acronym kind of implies, you have these graphics processing units. They are engineered, they are built to do graphics processing, and via some either originally software trickery or now via direct supported APIs, you can use them to perform general purpose computing. And that's all that's meant by GPUs. If we look back to effectively the version of the GPU that we ourselves have implemented, it looks something like this. Now, this is a proper NVIDIA GeForce 6 series architecture. It is extremely similar to what you have built. We have a vertex processor, our vertex shader. What do we skip, right? Well, we have our host interface. We have our vertex shader. We just have one of them. You could do two of them. I mean, it's just a matter of resources and debugging. We have an understanding of what needs to be done for culling and clipping. We don't implement that as a lab. We do all of the triangle setup, so we have that module. We certainly have our rasterization module. We have that built. We now have, at least to some extent via MP4, our fragment shading as well, with some mechanisms for doing texturing is something that as a team, several of you are currently working on. And then after all those fragments get processed, we have our, what we call our render output, Z compare and blend. So checking depth, checking alpha, determining what the final fragment should be in our frame buffer, and then that goes all out to RAM. So we do have that. We have an architecture that does this, and they are programmable. Now, in this era, early programmable days of GPUs, there were separate cores for vertex and fragment, and they were separate ISAs. They were similar ISAs, but they were still distinctly separate. You'd have to program your vertex shader via some subset of the assembly language, and then your fragment shader using a different variant of the same assembly language. But they could be used for programmable general purpose computing. In a sense, you were kind of tricking the GPU to do compute for you, but we have all the mechanisms now, and if you just want to think of your own simple graphics processor, that's fine. We have all the mechanisms now to do general purpose computation. Okay, it's slow because we just have the one shader core, and that's fine. And we have some restrictions in terms of what our data is going to look like. But another way to think about that, and there was lots of techniques and lots of research on how to do this maybe more effectively, we do have an ISA that allows us to do computation. Maybe it doesn't have exactly everything we need, but it has a lot, right? We can do some control logic, either explicitly via eventual kind of if statements and branch instructions, or more implicitly via things like our min and our max and our clamp and some of those other built-in functions. We have support for trigonometric functions for doing sine and cosine. We can calculate power. We can do basic mathematical operators as well. So we have the compute part as already. We have a kind of a challenge in this era of how do we get input data to look like the way we would want it to be, and likewise, how do we get output data the way we would want it to look? And generally what would happen back in this era is effectively you're basically fooling this architecture into doing a meaningless render. And in the process of doing that visually meaningless render, you're actually doing the compute that you're interested in doing. We can think of it from a texture mapping perspective, right? We know in texture mapping, we have this usually two-dimensional array of our data, and we want to apply it element by element in our fragment shader. We think of textures as being this visual thing, right? We have this checkerboard pattern, we have this picture, we have things we want to apply as our wrapping paper to a given piece of our geometry in our scene. But there's nothing really requiring that it looks visually like anything. It could just be data. And in terms of how we would do GPU back in this era, that's what we would have. You'd have a lot of code to kind of reformat data as texture, and then when it comes time to do your texture mapping, you'd still have effectively your text fetch type instruction in your fragment shader, but it was just using it as effectively as a general load store. You're grabbing an element from memory at this particular location, and then you're using that not to get a nice visual looking output, but to do some further computation on top of it. Another way to think about that is you have a texture, you can interpret that as a two-dimensional array, just a general matrix, and then you can do your matrix-based computations on that texture after the fact. We didn't talk about render to texture, but you could always have done that as well. Probably nothing preventing you doing that now in your own shader cores, but just arbitrary writing of data at the output of your fragment shader should also be possible, where you're providing an address, you're writing that address, so you could both have input as texture, output as texture, intermediate results as texture, and ultimately what you are doing is, yes, technically you're rendering, but you probably don't care at all about the scene itself. In fact, most common scenario is that you care about the amount of fragments and fragment shaders you'll be evoking when you execute a given scene. So you care about the geometry, but only to the extent it leads to a certain number of work queue or work objects and threads to be executed. So generally, in terms of what your geometry would look like, it'd be one big rectangle of a given size in screen space, and you would care, okay, this is going to be a 1,000 by 1,000 in screen space rectangle. That's going to lead to 1 million fragment shader threads, because there's going to be 1 million fragments post-rasterization. That allows me, to some extent, an ability to parallelize the workload across all these different fragment shaders. Yeah, the vertex shader is not doing much of anything, so that would be a pass-through. But you would generally have that imbalance already. We always have more fragment work to do than vertex work. So when the architectures themselves were discrete and with separate vertex and fragment shaders, you would have more of these fragment shaders, I'm pointing in the wrong place, more of these fragment shaders anyway than you have these vertex shaders, and you would kind of imbalance the work in that way. 4 vertices, make one big quad, send off 1,000, 10,000, 1 million work units off to the fragment shaders with input data as a texture. When they are then sampling from that texture, they're basically doing a two-dimensional data lookup into, let's say, a 1,000 by 1,000 array texture unit, texture array that you're interested in fetching, and then doing whatever further computation upon that result. And that was, when you hear the term GPU, that's what that meant. Kind of tricking the pipeline into doing a meaningless render with a meaningless or visually meaningless texture, and the end result is the end result of the computation you were interested in. We could probably do that ourselves at this point. The real challenges, and to the same extent those challenges still exist today, are when your data is formatted as a texture, there's those limitations. We talk about all the different types of texture formats, and all I mentioned last week was that they exist. You should support one type or two types at most, and just make sure that you have that type working. Part of all the different reasons there's these different support for textures is over time they were evolved to support different types of computational input as well. But in general, texture is meant to be a visual object, and so you think of data in terms of RGB or RGBA components. So part of the real task was kind of the pre-processing of data. How do I get my arbitrary data to do some arbitrary image processing or other kind of scientific computing task? How do I get it, and how do I format that as a texture? So there's kind of input pre-processing that's kind of a critical stage there. That's where the real complex code would ultimately kind of go in a GPU solution, and you have kind of the same output problem as well. I have outputted my render to a color buffer or a depth buffer or some particular buffer in my system. Now I have to read that back out and get some conversion function from that to the actual data output I am interested in. But that was GPU, and there was still quite a motivated community in terms of people working on that. This figure doesn't really show it because this is kind of the earliest programmable GPU architecture from NVIDIA. And when you have just, let's say, a half dozen of these fragment shaders or 8 fragment shaders, maybe it's not really worthwhile. This one's showing 16. But now when you can scale up to hundreds, now you do have a pretty impressive parallel computing chip compared to what was conventionally available for a commodity CPU at the same time. So the thought was, yes, you're kind of tricking it into doing computation when in fact it thinks it's actually rendering something to the extent it thinks at all. You're giving it a rendering pass in terms of the workload, but it's actually doing computation. But it was worth it. It was worth it to kind of hack the system in such a way because there was enough need and there was a market to build chips with as many of these things as possible for rendering tasks. We could then use them outside of their originally intended purpose and get good computational speed-ups. And it was all a hack. You were writing shader code or assembly code at the time, and it was a lot more work than maybe just writing an OpenMP or MPI type application. But on a single chip architecture, the benefits were potentially there because the resources for computation were there from the early days. More recently, and we're kind of in between in terms of what we implement in class, we have this concept of the unified shader architecture. Now, architecturally, there's almost nothing new here. So I'm going to talk about it, but if it makes a lot of sense to you because we've kind of been covering this as we've talked about GPUs throughout the semester, that is fine. Architecturally, we have talked about that already, and our ISA is already a unified ISA. The idea being that while one could design a static partitioning of how much chip real estate should be dedicated for vector shading versus fragment shading, with a couple tweaks and some innovation there, you can have just this pool of shader cores that could at some point be used for vertex tasks and at other point in time be used for fragment tasks. So you don't have to have that static partition. That partition of tasks between vector and fragment can be a dynamic thing and a scene by scene, even frame by frame potential basis here. So we have this unified shader architecture. Microarchitecturally, the cores still look roughly the same. What then also changed was, in parallel to that, was the recognition that people are using these devices for much more than just doing rendering. They're using them for computation as well, and this added this new interface, and you can think of it as just a software interface to the same exact flavor of hardware for doing general purpose computation. So if you hear the term GPU computing, and again, there's no board that decides, here's the term you must use for this, concept versus this other concept. But if you hear the term GPU computing versus GPU, that is the main differentiator. GPU, when you hear that term, although again, this isn't a hard and fast rule, you should be thinking of, okay, everything's a texture, and I'm doing kind of a meaningless render to kind of get some fragment shader cores activated to do my compute. GPU computing, we don't have to do that anymore. There's a separate API, a separate interface to the hardware that allows you to think of computational tasks first and foremost. You no longer, as the note says here, have to format your computation to fit into a rasterization-based rendering pipeline. But otherwise, architecturally, what the unified shader architectures in the compute view of what's happening is actually just a subset of what's already there for rendering. We're actually taking things away from the diagram, not really adding anything to the diagram at that point. With unified implying that there's a single programmable processor architecture, so it's the same exact underlying ISA for vertex shading, fragment shading, and general purpose compute. But as we saw when we were looking at GLSL, we have a lot of the things we need already in that for doing general purpose computation, right? We can do all sorts of math we may be interested in. It evolved to do lighting calculations very effectively, but it turns out the math needed to do lighting calculations is pretty general purpose, and we can use a lot of that and then do general purpose computation. The other big thing, and this has just been more a slow evolution than any kind of revolution, and I'll mention this in a couple of different contexts today, is just the scale of what amount of compute resources are available has continued to grow. Whereas in the more traditional CPU world, and you'll say if you take CPRE 581, we do have lots of multi-core, many-core kind of CPU architectures. But even for those, the type of core counts we are talking about are measured in the tens. Maybe some certain designs in the hundreds, but those tend to be very niche kind of specialty processors. You purchase a very nice Core i9 processor from Intel, you get 16 cores, maybe 32 cores depending on how you define a core here. There's a whole difference in order of magnitude between that on the CPU side, what you purchase for the high-end chips, and what you can get for the high-end GPU chips. Part of that is a terminology dispute. What does it mean to be a processor? We'll get into that a little bit, but again, there is no board that decides if you use the word processor, it must mean one particular thing. NVIDIA has changed many times over the years. What do they refer to as the individual unit of computation on their chips? And because these slides have been cobbled together over years, you'll see some different terminology that I am using. Streaming processor is a term that they used for many, many years. Definitely implied that there were, in this current day, 16K different little processors on the chip. Then later, the kind of marketing and technical documentation changed to refer to those as CUDA cores. Core also kind of implying that it's a processor as well. That's what we mean by that term. CUDA we will talk about here and learn a little bit more about starting today. Now if you look at documentation for Hopper class hardware or this RTX Ampere class hardware, they just refer to them as floating point units, which is probably the most accurate way to describe what there are 16,896 of on current class hardware. It turns out that's all that really matters because it can support lots and lots of threads in parallel. Really, the types of computation we're interested in porting to these kind of architectures can take as many of these as we can provide them. So having more still leads to proper speed up, still leads to proper benefits. Is it a processor? Is it a core? Is it just an ALU, like a floating point unit? Maybe it doesn't really matter at the end of the day. The truth is you can get that much amount of parallel computation out of the underlying architecture, but it's probably not fair to say that my Core i9 processor has 32 cores, but my NVIDIA GPU has 16,000 cores. It's not at all a fair comparison there, but no matter how you make that comparison, even if you just make it in terms of how many different functional units are there on chip of Intel versus NVIDIA, it's still an order of magnitude difference between GPU and CPU today. And the results kind of indicate that in terms of performance on computationally intensive tasks. So our focus will be on NVIDIA. Their documentation is still by far the best, and I would argue they're also the easiest to use. There are lots and lots of textbooks for those of you who want to learn more beyond what you can learn in this class. The material gets dated very quickly, and it's just a fast-moving field. Some code from 5 years ago will work, and a lot of code won't, and that's just that's the risk of being on kind of closer to the cutting edge of technology. So I actually don't recommend any specific textbooks. There is the NVIDIA CUDA programming guide. It is a hefty read. So you kind of have to start with like a hello world example elsewhere, and they provide the SDK that gives you that, and then that's still probably your best bet. So get hello world working, start to understand what features are available. We will get you to hello world and a little bit beyond that this semester. In terms of resources, though, when you want to go past that, I really can't recommend any particular book because by the time I put it on a slide, it's going to become dated soon afterwards. So the CUDA C programming guide gets updated with every incremental release of CUDA, and it's probably still your best bet. But having said that, this type of programming is not easy. So getting hello world to work, or like vector sum type examples to work, is relatively straightforward. There are some things that are new that hopefully you'll learn in this class, and you'll feel you've gained some knowledge here. But the fundamental challenge of how do I take a task, how do I make that task faster by parallelizing that task across 8 CPU cores or 16,000 floating point units or a cluster of machines or a cloud distributed workload, that's always going to be, I think, a challenging problem. So there is no magic wand in terms of what CUDA provides. It gives you the hook to say, I want to specify that I want my 1 million threads, just like we have the one big quad and we want to spawn off 1 million fragment shader threads. It'll provide you that. It doesn't really provide at all the solution for how do I use those threads in a meaningful way to get a appreciable speed up, preferably roughly on the order of the amount of work that I'm actually specifying here. That's still a fundamental challenge. It's not really something that we teach in this class. And for better, for worse, the type of class you'd want to look at if you really wanted to learn that kind of strategy, parallelization, optimization for software strategies, you'd want to look more in the high-performance computing community. Parallel programming is still the term a lot of people use for that general field. It's an old field, but I think the hard problems of old are still the hard problems today, and the easy problems of old are still kind of the same easy problems of today. Even though in that class you may not use CUDA, you may use something like an MPI or OpenMP or one of many different parallel frameworks for doing HPC-type programming. A lot of those classes still use Fortran. That's still state-of-the-art in all sorts of real-world scientific applications. The strategy of how we do that parallelization is what you learn in a class like that. They're kind of algorithms, they're kind of systems, they're kind of programming language classes, all kind of combined together. Those can be valuable if you want to learn how do I truly make my application faster. We'll learn the mechanics of CUDA. We'll learn and gain a more appreciation for underneath the hood, what we think best guesses as to what's happening here. But in terms of actually being able to parallelize applications ourselves, we'll touch upon it. We'll play around with a few examples. There is no quick fix for that. The easy problems have been easy for decades. The hard problems have not really gotten that much easier over time. The other big wrinkle, of course, is so many of these GPU resident tasks are related to machine learning applications, which can be thought of as a special case of your general parallel programming challenge you have. But on the flip side, they are recognized as being so important. There's whole separate kind of programming interfaces to take advantage of hardware to do machine learning more efficiently. We also have a class that offers learning more about how one does that, both in kind of the FPGA, bespoke, create your own processor, as well as understanding of best practices of accelerator designers, including in GPUs as well. And you can learn that with 487, 587 that's offered in the fall. So I mentioned that we were going to focus on NVIDIA and CUDA. It's what I learned first. It's generally what people learn. If you say I do GPU computing, that is still very much the default assumption today. Intel has their own frameworks. AMD also has their own frameworks. They've been a lot less stable in terms of the type of frameworks they've provided over time. There's Radeon Open Compute, which has a very CUDA-like interface that you can learn. There's also OpenCL, which is kind of gaining in prominence. It's very similar to CUDA. It's gaining in prominence, so I say much less popular. I refactor that to say less popular for HPC work today. I find it a lot more complicated. I think the reason is the goals are slightly different. CUDA is designed for NVIDIA GPUs, and it will work just well. This version of CUDA, this compute support on this GPU will work. OpenCL is meant to be more of a solution for all sorts of different types of accelerator architectures, from really big parallel high-performance clusters to individual GPUs, to custom accelerators using Xilinx or Altair or other type of programmable logic as well. And so there's a lot more you have to do to get Hello World working in OpenCL. A lot more careful management of computing resources that for NVIDIA you don't really have to do, because NVIDIA is taking care of a lot of that for you because their solutions really only work on NVIDIA hardware. That doesn't then mean that one is better than the other. I think it's fair to say, though, that if doing GPU compute, NVIDIA, CUDA, still very much the way to go. check back in a couple years, see if that landscape has changed. But so I think, long story short, we're on pretty sound footing in saying we're learning GPU compute, we're learning CUDA. It's technically less open in some ways, but it's so much more ubiquitous in the space that there's a lot more resources to learn than if we were to start with OpenCL. This is the first example architecture, NVIDIA G80, that had the unified streaming processor. At a very high level, conceptually, the thought was, if the future of GPUs is around programmable processing, we're going to build the architecture around the processor. If the past of GPU architectures was on rasterization-based shading, we build the entire architecture around the rasterizer. If the future is just programmable processing, then it's the individual processing cores themselves that are paramount. And so this is still a rasterization view of the G80 architecture, but this is it with the unified shader cores in place. And that's what these little green boxes are meant to look like here. Otherwise, though, and we've brought up a version of this picture in the past, otherwise I think we can still squint at this and see our SGP architecture, although we've made some slightly different design trade-offs here. Host, input side, get our vertices. Now it's vertex thread issue. That is now, once we've fetched all the attributes for a vertex, that now becomes a software thread. We kind of do the same thing, right? We're kick-starting an invocation of our vertex shader when we have a new vertex coming in. There is a lot of hidden complexity here in terms of who is either kicking off those threads or managing all of those threads. There's dedicated hardware that takes care of that. I have a new vertex that comes in. I have a reasonably large array of these streaming processor cores that I can execute my next vertex shader logic on. And somewhere, some piece of logic is determining, okay, you're next, you're going to go right here. That does depend, and that has changed over time in terms of what type of benefits can be had by having like vertex threads be shared on like streaming cores. But in general, there's some sort of logic for doing that kind of thread management. So this is executing on these cores. We'll talk a lot about detail of what that means underneath the hood, but here's texture fetch, and everything is ultimately just an access to then your memory interface. Your memory hierarchy of texture fetch unit is doing your sampling. That's going to then hook up eventually to your memory hierarchy of your L1, L2 cache to go off into your DRAM at the end. Not really shown here is at some point our vertex shaders have completed. Someone is kind of collecting the output attributes of those vertices as they are completed. They are grouped back together. Now we're back to our rasterizer. It's still there. It hasn't disappeared. We then do, that's our setup. That's exactly what our triangle setup is, right? We do some primitive assembly. We figure out the gradient-related constants to be able to do our rasterization, and then we generate fragments based on that, and that's what's happening here. The main difference between this picture, and sorry for scanning quickly, and this picture is we can kind of view this as kind of a top-down flow here, because we did have vertex shading, then to this step, then to our fragment shading, finally to our render output. And here we no longer can really do it. It's a feedback loop, or at least it's a single cycle here of vertex threads come in, we collect the results, we then rasterize, fragment threads get generated, and fragment shading takes place on the same exact hardware. And there's no restriction that you do all of your vertex shading, then you do all of your fragment shading. You have a certain pool of these cores that are available to get the next set of instructions to execute on them, and there's thread managers that take care of that. Okay, we've received 3 vertices, we can generate a triangle, let's get those fragments going, and it's all kind of happening in parallel with each other. Otherwise, though, and here it's kind of trying to show like the render output stage is kind of a less influential part, but it's still doing some of the same critical things of depth checking and alpha blending. But otherwise, it's really not that different than what we have. We could have built one that basically just had 2 of these little green boxes, and that's very close to what's in your simple graphics processor. The other big caveat is once you go from 1 thread to two threads, that does change the complexity, right? We don't have to manage threads because we just have 1 at any given time. So there isn't anything to manage. We start, we execute, we finish, we restart, we execute, we finish. Now when you're managing potentially thousands of these threads, tens of thousands of these threads in parallel, there is a lot of extra complexity to keep track of that. But a thread and I think you've all taken operating systems and related courses. Okay, James got nervous when I said that. The only thing you need to remember from that class, a thread or a process is just a storage of the metadata to get back to where you were in the execution of that piece of work. So from our perspective as architecture people, and you've made it far enough this semester, you're all architecture people now, register values, program counter, flags if necessary. That's pretty much it. And and the program counter corresponding to some instruction memory space. That's pretty much it, right? So when we talk about managing threads, yes, in your implementation, you're not really having to do much managing of threads. But if I said you have to support that, you have to support 4 different threads at different points in execution, well, if each of those 4 threads were executing totally different types of code, different shaders entirely, that would be kind of challenging. Now you have to make sure you're swapping out instruction memories, you're really clearing all the contents out as you go. But if the restriction and the limitation was each thread is doing some version of the same exact thing, then a thread is really just some registers and a program counter. Where am I in this instruction stream? Am I on instruction 1, or did I make it to instruction 10? Wherever I am, I'm going to stop, and if need be, start back up later. You change the registers, you change the program counter back, and you've got your state. You've done that context switch. You've recovered back to exactly where you were. That limitation sounds very extreme, but in the context of graphics, it's very natural. Because we are doing just the same thing over and over and over again. If it was truly general purpose, in the sense that your Intel processor is capable of it, where Core 1 can be doing something completely different than Core 3, completely different than Core 3, totally different programs managed by a proper operating system, they can share, they can communicate, or they can be completely independent from each other, then that thread management becomes a much more complicated thing. You need a proper operating system and scheduler and all the complexity that goes into that in software. If our limitation is, and it is kind of a natural limitation, that everything's basically doing the same task. They may be at different points in the same task. Here, we may have just started doing some vertex transformations, but here we're maybe in the middle of doing our fragment shading and figuring out textures and lighting and things like that. They could be at different points in the same task, but they're all basically dedicated to the same task. Then that challenge of how do I manage all this complexity, how do I manage thousands of threads, becomes a lot easier. If you think of thread as just in this context, just the program counter, maybe some registers, some flags and things like that, a very small amount of data basically is what you're storing per thread. And if you're limiting each thread to then doing the same exact task and just being at different points in that same exact task, you can maybe start to see why we can have a GPU with 10,000 cores on it, for whatever your definition of a core is. Because we've stripped away a ton of what makes your CPU core much more general purpose than what this is. So it's not a free lunch. We're not getting 10,000 cores. But it's not, the engineers at Intel are not lazy or anything like that. Right? It's nothing to do with that, right? It's this difference in perspective in terms of what it means to have a particular thread. What is an individual thread meant to be capable of? And here, because of the graphics context, we're always doing rendering. We're always running the same shader or pair of shaders or a small collection of shaders at any one given time. A thread can be this extremely lightweight thing. That's on the graphics side of things. When I now show the same architecture with the compute mode of what's happening here, all I've done is take away things. I haven't added anything to this diagram. The main takeaway from a programmer's perspective is, okay, with rendering, I can have these hundreds or thousands of threads because they're all being kind of forced to work on the same type of work, do the same type of work. You're always doing this vertex shader, this fragment shader. If now, for my more general purpose computation, if I enforce effectively the same exact limitation, which is, do some general purpose computation, but everyone has to kind of do the same general purpose computation at any given time, then you can have these thousands of threads. Then we can basically use the same exact architecture. Then there is really no difference between doing vertex shading or fragment shading versus compute shading. You'll maybe hear that term. That's an OpenGL specific term of a different type of compute shader. Usually, if you need to do compute in the service of a broader graphics application, you may use an OpenGL compute shader. If you're just using compute for the sake of accelerating some software application, that isn't rendering related, then you would use a CUDA shader. But they're basically the same thing in terms of what features they support. Now we don't think of things in terms of vertex fetching and rasterization and generating of threads and that mechanism. Now, and it's presumably the same exact piece of hardware here, just relabeled as thread execution manager. Now we're being told we need to execute this many number of threads, go launch them, collect results when they are all done. Now, in terms of what our interface is to memory, it is the same still physical hardware here. You can still have textures, but whether you do or not, you can have textures in your CUDA calls. Otherwise, though, we think of it as just a general load store architecture. You have a thread, it's got its program counter, keeping track of where it is in the instruction stream for that set of threads you're executing. At some point, you need to do loads and or stores, and you start to access the memory hierarchy via your L1 cache and moving on beyond that if need be. But otherwise, although things are kind of relabeled and moved around here, what's different between using this architecture in compute mode versus using it in graphics mode is what we don't engage. We don't need the rasterizer. This is why I haven't really been able to provide a very satisfactory answer as to, is the rasterizer still a physical thing? Is there like a region of chip that is the rasterizer or not? There probably doesn't need to be. It can presumably all be done via some kind of micro-coded software. But still, what we have here between this diagram and the previous one is what we've removed. Is we don't need to have anything that's really vertex and fragment specific anymore. We don't have to trick it into doing computation. We just make sure that this module itself has the ability to just launch threads independent of any graphics context. Instead of worrying about, I have a quad of this size, rasterize it and give me this many fragment threads, it's just give me this many threads to do the same computation. Otherwise, though, architecturally it's the same. So your simple graphics processor can do GPU compute to some extent, right? The trick for us then is, well, we hard-coded a lot of this stuff because, we have limited design cycles for the host interface and how we're doing the assembler. We certainly hard-coded this. And then, for better or for worse, as a design decision, we hard-coded this kind of arrow in this diagram here. Those were, design decisions made because of limited resources and time to build up such infrastructure, time for you to work on it. But otherwise, and we only support very few instructions as well, also due to limited time and resources. Otherwise, we can effectively support this as well. This is the G80. Today, if we look at the GA100, there are some important differences. So when I keep kind of implying that it's just more of the same, that's still mostly true. The biggest difference between G80 and GA100, which is still roughly in terms of what you can purchase today, kind of the highest end part, really just a significant increase in the scale of what is able to get fit on chip. It is more a VLSI innovation than an architecture innovation. This is certainly an architecture innovation in terms of supporting unified shaders, supporting compute mode as well. This is also architectural innovation, but it is much more so VLSI innovation than or semiconductor innovation than it is architectural innovation. It is effectively, you can't see it because the scale is so much more, it is effectively much tinier version of these same green squares being shown in this particular diagram that's happening here. So we can learn based on this or somewhere in between and not really lose a lot of generality in terms of what's happening here. With each major revision, there are additional features, either different types of instructions that can be supported or custom support for different classes of somewhat general purpose computation that is supported. And there are changes, there are innovations, there are things that only work on this hardware that wouldn't work at all on the older hardware. But for the most part, it is a scaled up, cranked up version of the same basic design. The real innovation happened with the evolution creation of CUDA and the supporting devices. Since then, that's gone from CUDA 1.0 to, I don't know what we're up to now, either 11 or 12, really just more of the same. So let's talk about CUDA. In the early days when these devices were programmable, it was effectively via assembly programming. And NVIDIA still provides this kind of virtual ISA with a programmer's interface if you want to either view what's happening or directly specify the instructions you're interested in. That's referred to as PTX, or Parallel Thread Execution Assembly. It is a virtual assembly in the same sense that x86 has become almost a virtual assembly, in that there is further translation that happens post-compile, post-execution, where it gets translated to lower-level assembly, which is only somewhat documented and open. We generally don't do assembly programming anymore, like we don't do outside of very specific needs, perhaps in the embedded space. We also don't do assembly programming for GPU compute anymore, so that's why we have the so-called CUDA extensions, these high-level, relatively high-level programming extensions. It is effectively originally a C++ extension, but now there's CUDA support in basically any language you're interested in. Because as we'll see, CUDA doesn't really add all that much. That's kind of the beauty and the value of it. OpenCL, just by comparison, is entirely in C++, but it is such an opaque and templated C++, it is very hard to get from 0 to 1 in OpenCL on your system. When we look at CUDA, there are a couple things that break pure C or C++ compatibility, but once you have a handle on, so you have to use NVIDIA's compiler, but once you have a handle on that, you're really good to go. You're really good to go with comfort programming language that you're familiar with, which is why, while it is nice, there's MATLAB bindings, Python bindings, Go bindings, Rust bindings, bindings for every language you may be interested in. That's actually not that great of an accomplishment, because there isn't really that much that's beyond native support from the compiler for that behavioral language. We will focus on the CUDA C, C++, because that is the primary mechanism still by which people do CUDA programming. The key concept that we've already kind of briefly touched upon is that you're going to have thousands of these threads, and you generally want to have a large number of threads because you have an architecture that looks something like this. And the whole point is to keep it full, right? To keep it happy, to be using it effectively. So you want to have applications that you can think of breaking down into thousands and thousands of subtasks. But all of those threads, by and large, are going to be executing a single kernel in parallel. They're all going to be on the same instruction memory stream. They're allowed to be at different points in that instruction memory stream so they can have different program counters. But with that restriction in place, and there's some further restrictions we will talk about, you get then effectively, quote-unquote, free context switching between threads. If the term you may have heard in other contexts is SIMT, for single instruction multiple thread, which is somewhat different than single instruction multiple data, that's effectively what it's referring to. Basically, vectorized compute, where you can do a lot of your floating point math in parallel, and you can switch between these threads, but it's because they're all running from the same exact instruction stream. So there isn't a lot of context switching to happen. We have to basically tweak a couple registers, a couple flags, change the program counter. We've now switched from thread 1 to thread 2 on that same CUDA core. So some of the CUDA design goals. So scalability is a very nice feature. It's one of those things that's nicer in theory than it is in practice. You can run reasonably old CUDA code and it will still work to some extent, but to really take advantage of what you need to have an underlying assumption and understanding of what is my actual architecture that I'm executing on. And it does allow, and this has been where some of the innovations have happened in more recent years, more clever ways of handshaking and interfacing between the CPU side and the GPU side. It used to very much be kind of like how we kick things off now in our own simple graphics processing architecture, where we say CPU sets everything up, tells the GPU go, and waits for the GPU to be done or monitors the GPU status. That was still effectively the case in early days of CUDA, and now there's lots of support for kind of parallel compute streams here. That code becomes very complicated to think about in terms of what kind of parallelism is possible, but the hooks are there for it as well today. Some of the terminology, and I've been using it a little bit all semester, so hopefully this doesn't sound that new today. This is the CUDA terminology, everything that's kind of highlighted on these subsequent threads here. So a parallel program are executed as kernels. So kernel is not a term they invented. It refers to like a standalone piece of logic, but those are what we refer to as what's being executed on the GPU at a given time. The other term for GPU is device. We've been using that term, I think, this semester, with host referring to the CPU that is in companion to it. This is a restriction early days of CUDA, which is a little bit less true today, but I think a good mental map to have still today going forward is think of it as there being just a single kernel executing at a time. I say that's not literally true, so I'd be a little careful. You're allowed to subdivide different subsets of the chip and allocate one kernel for one subset and another kernel for another subset. So you can do more than one kernel at a time. But in terms of the individual application you are writing, thinking of it as being just a single kernel at a time is still kind of the right computational model to have in mind. So a single block of code is what you are executing, and all of the threads that you are then spawning and telling to execute are going to be executing that same kernel code. And that requires us to have a very similar kind of mental model to what I think we already had for vertex and fragment shading. And maybe there it was more natural because I just told you that's how you have to think about it, and you didn't think otherwise. Each vertex shader that you write, by and large, is only aware of itself, is only aware of its values for its attributes. It's kind of stateless in a sense then, right? I take a vertex as input, do some transformations on it, spit out a vertex as output. I don't know what's happening in my neighboring vertex. I know my vertex. Same for fragment shading by and large, right? I take my fragment as input, I do some math on it, generate a fragment or modify that fragment and specify that as my output. So each fragment shader and each vertex shader are already written from a single vertex or a single fragment's perspective. So we already are kind of doing that because while they can be executed in parallel, they don't need to have any actual knowledge about what the other neighboring vertices or fragments are up to. That restriction is kind of natural in the rendering side of things. Now that same restriction, because it's using the same exact architecture, is already in place, is also in place for the GPU compute side of things. You have this kernel, you're executing thousands, hundreds of however many threads in parallel, all executing that same block of code. So now that kernel, when you write it, it has to be written from a single thread's perspective. It is not generally aware of what the other threads are going to be doing. And that itself is now a little bit different when we think about how we do computation, how we think about multi-threaded parallel computation. We think of kind of embarrassingly parallel problems versus more subtle data sharing parallel problems. You have support for some of that in CUDA. You can synchronize between blocks of threads at a given time. But in general, when you write that kernel code in CUDA, it's a single thread's perspective. A big chunk of your CUDA code, it's not exactly boilerplate, but it tends to be doing a very similar task, which is I'm a thread. Which thread am I is part of what the boilerplate is there to determine. What work should I specifically be doing amongst all the work that has to be done? Vertex fragment shaders don't have that problem. They have an input attribute stream, right? Here's your work, it's the vertex, or here's your work, it's the fragment. Do what you need to do. We're not doing graphics processing anymore for that, right? We're doing general purpose computation. Now, big part of the responsibility as you write that CUDA kernel, the code for the C/C++ or Python, whatever code you write for that, is to determine what work should actually be done on a thread-by-thread basis here. Part of what we're going to use for that purpose is, as part of that thread manager, when we execute a thread and the mechanism by which we spawn all the threads we are going to execute, it gets provided an ID or an index, however you want to think about it. They're both valid ways of thinking about it. But an ID, it gets its own little name badge that says, you are this particular thread. And so a big part of usually the prefix part of your kernel and kind of the end of your kernel is, okay, here's my ID, here's what values in memory I should be working on. Likewise, I've done all my work on those values, here's my ID, here's where I should be writing my end results to. And that mechanism is what allows that to happen. That as we spawn these thousands of threads, they each are going to get spawned with, I mentioned some register values. Part of that is, here's a unique ID for each individual thread. You write the code, I'm kind of anthropomorphizing them, but you write the code so that the code is aware on a thread-by-thread basis of what its ID is, and it does that work correspondingly to that thread, or relative to that thread. Here's a very simple example, but in a sense, if you understand this, you're good to go to get started with Hello World. So let's go a little bit slower with this. The first thing you may notice, this is our C code, and there's really nothing here that couldn't be compiled by a C compiler, is it looks a lot like a function, and it kind of is a function. And we have to be a little bit careful because there's still this concept of functions. You can have kernels that call functions and whatnot, but in terms of syntactically, our interface to writing kernels, it is very similar to our mental model of what we do when we write a function. That we have inputs to the function and we do some work based on what those inputs are. Two main differences, I guess, that you want to think about when you're writing kernels versus when you're writing just regular functions in your code. In kernels, there's no real concept of a return value. The function doesn't return value. This piece of hardware is checking when the thread is done, but that's about it. It's not really checking and grabbing some result from that thread as it's executing. So they're almost certainly, if they're actual kernel calls, going to be void functions. Global is just the keyword that NVIDIA used to distinguish between host code and device code. They're going to be these global void functions. They're not going to be returning anything. But we need to output data, right? We need to actually change some state in the system for our kernel or our thread to be useful. The most common mechanism for that when writing CUDA code is to treat all the inputs to every one of those threads as the same exact value. So again, this is a piece of logic that's going to be executed tens, hundreds, thousands of times. They're all going to be passed the same pointer. And so we do so usually via pointer mechanism, right? A pointer is just an address. So we get a base address to some input array, we get a base address to some output array. And so they all get that as their input. First thing to then recognize is, be a little bit careful with the names. These are both inputs to the kernel, and the name of those variables kind of gives away what they're being used for. This is our input data. Since they're pointers, we can always just kind of write to those values and update memory as a consequence of executing our code. So one or multiple of those will be used as the output of that kernel. We don't return something from the kernel. We're updating values in memory, generally is how we get a so-called result from executing our kernel. That's the second thing. So your kernels are going to always kind of look like that. Maybe they'll have a lot more inputs, but in general, pointer to some input data, a pointer to some output data. The other thing that we then have is these thread indices. Think of them as the badge, the ID for each individual thread. The mechanism by which those get assigned we have control over, but we still have to talk about. So I haven't talked about that yet, but they have them, and as they're executing, they will have access to those in certain dimensions. This can start to look a little bit like your swizzle operators, right, with your x.xyz, and it's based on the same mechanism here, where you have a multi-dimensional layout of our threads. You can then have a .x, a .y, a .z for your thread index here. And we use, as we develop our kernels in CUDA, those thread indices to kind of pick out, proportion the subset of the total amount of work for each of the individual threads that are going to be executing in parallel. So this kind of mechanism of I call it kind of like the bookkeeping work that's required here, but kind of the input bookkeeping of, okay, I'm a thread, I need to do something with the input. In this case, it's a simple example where there's just a block of threads. I'm going to take my x dimension of my index, and that's my offset into my pointer. This is arbitrary, but this is one way of doing it. Each thread in a single block of threads is going to be guaranteed to have be a little careful with what I'm saying here. If it's a one-dimensional block of threads, each thread is going to be guaranteed to have a different value for thread index.x. That only works if it's one-dimensional. We can have multi-dimensional blocks, but ultimately, we take our .x, potentially our .y, and our .z, and it's going to become up to a six-dimensional problem, which is why the code is not trivial for doing that. In this case, it's going to be our first example is a one-dimensional layout of threads. And we grab that dimension, which is going to be a unique value for every thread that we're executing here. And we use it to index into both our input as well as ultimately into our output. Afterwards, we've grabbed a value. This is a local register or a local value for that individual thread. We do something with it. Now that could be any other kind of function. We don't care what it's doing, but we're doing something else with that input value to get an output value y, which we then update in our memory. If you've got this, you pretty much have what you need for CUDA. There's some other wrinkles associated with that, with how we're actually going to be executing our threads here. But these are basically the 4 changes when going from kind of standard C/C++ to CUDA C or CUDA C++. We have the function type qualifier, that's our global keyword to specify where this function, who's supposed to be compiling this function, where is it going to be resident? Is it on the host, on the CPU, or is it on the device? Is it on the GPU? There's also lots of ways we have to manage the various memory regions in our device, and there's keywords for that. There's the directive to specify how we're going to launch this work, and I haven't talked about that yet. And then there's the built-in variables, of which we've seen the first example called thread index. This is a built-in, gets assigned by the thread manager, that specifies both the dimensions of our layout of threads as well as the individual indices for our individual threads here. This example is from the CUDA SDK, and it's about as simple of an example that you'll be able to find here. We will talk about more of this as we go, but your CUDA programs are going to look a lot like this. Likewise, as your OpenCL programs are going to look a lot like this as well. We have to do some memory allocation, some host-side memory allocation. In this case, here's A, B, and C. We then separately, I should be able to find it, we then separately have to do memory allocation on the device as well. We'll be talking more about these functions. We have some block of data on the host, corresponding to inputs, perhaps output values. We also have to allocate buffers on the device as well. We also generally have to do that when we're doing graphics code, but a lot of those are kind of hidden underneath the hood of using a windowing system. When we use GLFW, it's doing a lot of device memory allocation for us. We just don't see those details. Now, we are responsible for determining and copying memory directly over. Those are 3 allocations. Copying memory over from the CPU's RAM to the GPU's memory. You can kind of, even if we haven't talked at all about CUDA malloc, you can kind of figure it out, right? What's happening there, right? Likewise, we haven't talked about CUDA memcopy, but you can kind of figure that out as well, right? There's no mystery there what would be potentially happening with those functions. We allocate buffers, we copy buffers back over. This is the part we will talk about still, but this is the other main feature that even my syntax highlighter here, I may not have installed the right one. It says CUDA C++. It doesn't look very syntactical, but this is our kernel launch. It's not quite a function call. It's intentionally using syntax that's not valid C or C+ otherwise to specify, here's the name of the kernel I want to launch. Here are the parameters of how many threads I want to launch. And we'll spend all of Thursday talking about the different possibilities for those parameters here. We can actually see it if we're interested. Somewhere num elements was defined up above. 50,000 elements, that's the size of our vectors. We're going to take 50,000 and basically split it into 256 chunk blocks. So that's fine. And so we're going to create a layout of 50,000 threads, basically, is what this example would be doing. So there you have it. It's a little messy, but that's 256 threads per block, and then 50,000 divided by 256 total blocks. That gives us 50,000 total threads here. That is not inputs to the kernel, but that's laying out the dimensions of the launch of that kernel. And then we do then have the inputs to the kernel. Those are going to be your pointers. It was called input and output in the other example, but now it's, data A, data B, data C as our values. We launch the kernel. We can, in theory, do things in parallel, but otherwise we kind of have a blocking call to wait for it to finish. Then we copy the results back out, and I think this does some checking to see, for this, did we get a result that's actually correct, that within range of what the host would have been able to calculate. So a lot of these CUDA SDK examples are intentionally kind of, they're unnecessary in the sense that we launch a kernel to add 2 vectors together. Then to check if the result is correct, we manually add the 2 vectors together anyway. So, it's not really speeding anything up, but just to test that things are working is more important than anything else. And then here in this case, sometimes it's put in different files, other times it's just top of the same file. We have our actual CUDA kernel here, global void, so it's not a function call. Name of the kernel, pointers for our inputs and outputs here. And in this case, there's a little check to make sure, because it actually technically is launching a few more threads because it doesn't divide evenly by 256. But otherwise, ignoring that if statement for now, based on my kind of bookkeeping code of which thread am I, we will talk about on Thursday the end result of that computation of that first line in the kernel is every single thread, all 50,000 threads, are going to have a different value for I at the end, from 0 to 50,000. And consequently, each thread is executing the same exact code, but the only difference is the value of I. So they're each taking one element in that array and just adding A and B and calculating C. Probably not going to be faster than doing it in hardware or in regular software, because there is some overhead in launching all those threads and collecting all those threads, and we're only doing 50,000 pieces of work. But at least this shows that it actually calculated and got the correct result at the end of the day. So please come back on Thursday, and when we do so, we'll work on some kernels ourselves. And I skimmed over this part for now. Recognize that these are kind of built-in variables. These are unique to CUDA that tell you the dimensions of the thread layouts we're spawning, as well as for each individual thread, its own index into those dimensions. And we almost always are doing something like this, either at the beginning, or if not the beginning and the end of our CUDA calls, our kernel calls, to do our bookkeeping, to say, I have all these threads. We can have all those threads because they're really just one instruction memory, right? One block of code they're executing, and each thread is really just a program counter at the end of the day. Program counter plus these variables at the end of the day. Each thread is executing the same exact code. We have this bookkeeping code at the beginning to give each thread a certain amount of work. That doesn't require that each thread does exactly just one thing, but each thread is going to be responsible for one block of work that it's going to be doing. That requires you to think about the type of problems you would implement in CUDA a little bit differently than if I said, here's a cluster, run this MPI code, have a completely parallel solution to it, because only certain problems are going to map to that kind of mental framework for how we do parallelization. If I want this part of the task to go completely down this path, this other part of the task to go completely down this other path, you can write CUDA code that will do it. It's not going to be very effective, very efficient. We get these benefits by limiting what our cores are basically capable of doing independently from each other, and then we get those benefits by scaling up to a very, very large number of those cores. If your task matches that, you're going to get really impressive speedups by doing it in CUDA. Let's leave things here for today, and we'll do some more examples starting on Thursday. Thanks.